If NASA called a press conference tomorrow and said, "We're moving an asteroid," would you feel safer? Or would you immediately think, "Wait, can they accidentally push it into us?" Because here's the wild part. NASA has already changed the orbit of an asteroid on purpose. Not in a movie, not in a simulation. In real space, with a real impact, measured by real telescopes. And the part that should grab your attention is this. The asteroid they hit wasn't even dangerous. That wasn't the point. The point was to prove we can do it before we ever have to do it for real. Now, quick pattern interrupt. Most people imagine the planet-killer asteroids, dinosaurs, global firestorms, the whole Hollywood package. But the more realistic threat to humans isn't a 10-kilometer monster. It's the mid-size objects that are harder to spot and still big enough to ruin a region or a country. In 2013, a roughly 20-meter asteroid exploded over Chelyabinsk, Russia. The shockwave injured about 1,500 people, mostly from shattered glass. That object wasn't even detected before it hit. It arrived from the direction of the sun, where telescopes have a hard time seeing. So when NASA talks about planetary defense, the first fight is not deflection. The first fight is discovery. Right now, NASA and its partners watch the sky with survey telescopes like Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, and Atlas, telescopes designed to catch fast-moving, faint objects. Then NASA's Center for Near-Earth Object Studies at JPL runs precise orbit calculations, and the Sentry Impact Monitoring System keeps updating risk lists as new measurements come in. And here's the uncomfortable controversy that almost nobody says out loud. We are still finding new near-Earth asteroids all the time, and many of the ones we haven't found yet are in the size range that could flatten a city. NASA has found the vast majority of the kilometer-class asteroids, those civilization-level threats. But for this still catastrophic 140-meter class, we're not done. Not even close. Depending on the estimate and the discovery rate, it's roughly in the "we've found only around half" or less territory. Meaning the real defense plan begins with a simple, terrifying question: what haven't we seen yet? That's why NASA is building a mission specifically to find them. NEO Surveyor, an infrared space telescope designed to detect asteroids by their heat, not just reflected sunlight. Infrared matters because dark asteroids can be hard to spot in visible light, and because a space-based viewpoint can search parts of the sky that ground-based telescopes struggle with. But let's say we do our job. We find an asteroid on a future trajectory that could hit Earth. What happens next? This is where Hollywood absolutely ruins people's expectations. Because the real strategy is not wait until it's close, then blow it up. The real strategy is touch it early, nudge it slightly, and let time do the rest. An asteroid doesn't need a huge push. If you can change its speed by even a tiny fraction when it's still millions of kilometers away, over years that small change becomes a giant miss. The key resource isn't explosives. It's time. And NASA's most proven technique so far is the kinetic impactor. Smash a spacecraft into the asteroid at high speed to change its motion. That's exactly what NASA tested with DART, the Double Asteroid Redirection Test. On September 26, 2022, DART slammed into Dimorphos, a small moonlet orbiting a larger asteroid called Didymos. This system was chosen specifically because it posed no threat to Earth, and because changing Dimorphos' orbit around Didymos would be measurable from Earth. DART's spacecraft mass was about 610 kilograms, and it hit at roughly 6.6 kilometers per second. Here's the moment that should make you sit up. The goal was to shorten Dimorphos' orbital period by at least 73 seconds. It changed it by about 33 minutes. Not seconds, minutes. That result wasn't luck, it was physics, and it revealed a crucial bonus. When DART hit, it didn't just transfer momentum from the spacecraft. It blasted out a plume of ejecta, rock and dust that shot off into space. That ejecta acted like a thruster in the opposite direction, amplifying the push. Scientists call this momentum enhancement, and after DART, Analyses indicated the impact was several times more effective than the spacecraft's momentum alone because of that ejecta rocket effect. And we didn't just think this happened. We watched it. NASA's Draco camera streamed the final approach. Telescopes on Earth tracked the brightness changes to measure the new orbit. Hubble and the James Webb Space Telescope observed the debris. And an Italian companion spacecraft, LIC, flew by and photographed the aftermath from a different angle. So yes, NASA can deflect an asteroid. But now for the second pattern interrupt. Success creates a new question that's almost uncomfortable. If we can move an asteroid, who gets to decide when to do it? Because deflection is not just science. It's geopolitics. A small change early can turn an impact into a miss, but it can also shift the risk corridor, the line of possible impact locations, across the planet while you're still refining the orbit. That means planetary defense decisions require international coordination and transparency. This isn't one country saving the world. It's the world agreeing on the plan. That's why there are international groups like the International Asteroid Warning Network and the Space Mission Planning Advisory Group, which coordinate observations, communication, and potential mission responses among space agencies. The nightmare scenario isn't only an asteroid. It's confusion, misinformation, and delay. Now, what about the famous nuclear option? Yes, it's real, in the sense that it has been studied seriously. And no, it's not the movie version where you drill and explode it into neat, harmless chunks. A nuclear device could be used as a standoff explosion near an asteroid to vaporize part of the surface and create a strong push. It's potentially the only option for very large objects, if discovered late. But it comes with massive technical and political challenges. Fragmented debris could still threaten Earth. Predictions depend on the asteroid's composition, and the global consequences of launching nuclear payloads into space are complicated. So NASA's approach is layered. Detect early, track precisely, deflect with the simplest reliable method, and keep higher-risk options as a last resort. There are also slower, gentler ideas that sound like science fiction but are actually grounded in physics. A gravity tractor, where a spacecraft hovers near an asteroid and uses its own tiny gravitational pull over years to tug the asteroid's path, or surface-focused methods like targeted ablation, where energy causes material to jet off like microthrusters. These aren't the headline grabbers, but they're part of the real conversation. And here's the irony that flips the whole story. We don't need a superhero moment. We need boring, relentless preparedness, cataloging objects, improving orbit predictions, running drills, and building the ability to respond years in advance. Because the real danger isn't that an asteroid is unstoppable. The real danger is finding the right one too late. So when you hear NASA deflects dangerous asteroids, the truth is even more interesting. They're building a system where the asteroid never gets the chance to become a last-minute emergency. If you want more science explained like this, real missions, real data, and the moments where space gets uncomfortably personal, make sure you follow for the next one. Now tell me in the comments, if a real impact risk appeared and deflection could shift the potential impact zone across different countries, who do you think should have the final say on when NASA pulls the trigger?